This is the continuation of part 1 of the Chapter 6 review. Halfway through part 1, part 2 is yet to come. Alright, so here we go. Picking up where we left off last time, we're now on number 40. So we're looking for all the functions given that the cosine of theta is 12/13ths. And theta is between 3/2 pi and 2 pi. Well, first of all, let's locate this angle. It's between 3/2 pi and 2 pi. Let's review. This, of course, is 0. And we're going around to, this, of course, is pi. And all the way around would be another 2 pi. So if this is 0 and this is pi over 2, we're going through the logic of how you can identify these positions if you don't remember it on the spur of the moment. So we have 0 to pi, therefore this is a 1/2 pi. That makes this, by the way, a 1/4 pi. Well, let's count by fourths. We have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 6/4 pi. That's known as 3/2 pi. Okay. So this angle is between 6/4 pi, or 3/2 pi, and 2 pi. So the angle is someplace here in quadrant 4. Exactly where in quadrant 4, I don't care. I simply know it's in quadrant 4. By the way, I could have counted by halves instead of by fourths. Is that 0, 1/2, 2/2, 3/2, same thing, 3/2 pi. We'll have more review later on how to find the 30 and 60 degree angles. We'll do that in part 2. Alright, so we know the cosine is 12/13ths. Of course, we have our old friend, so, toa, cosine being adjacent over hypotenuse. So the adjacent over the hypotenuse is 12/13. 12/13. Now you could use the Pythagorean theorem to find the missing side. A squared plus the unknown b squared equals c squared. Or you can simply remember that if you've got a triangle, a right triangle, with a leg of 12 and a hypotenuse of 13, then the other leg has to be 5. How am I supposed to know that? Well, that's a combination, a ratio that's worthy of memorization. Just like 3, 4, 5. Also, 5, 12, 13 needs to stick in your mind. It can come in handy. It's another memorizable ratio in right triangles. So we know that the opposite side here is 5. Our theta, of course, sits right there. So from there, we're practically done. Sine, opposite over hypotenuse. Sine, opposite over hypotenuse, 5/13ths. Let's go to this now. Tangent, opposite over adjacent, so we've got toa, OA. Tangent, opposite over adjacent, that's 5/12. Oops. I'm ignoring the fact that the 5 is negative. Or tell you what, let's continue to ignore that. Let's just remember that all students take chemistry. So in the 4th quadrant, cosine is positive. Everything else is negative. Cosine is positive. Everything else is negative. Or we can see it by the fact that this is negative 5. You may remember, and this will come in handy for number 97 of part 2. Yes, there's a number 97 for part 2, but fear not, it's still a short assignment. Do you remember how to find the coordinates of that point? Well, that's easy. 12, -5. 12, -5. Then do you remember the old definitions of sine, cosine, and tangent that we had back at the beginning of this chapter? That sine is the second coordinate, which is, oops, I'm sorry, that's assuming a unit circle. Oh, I messed up on that. This is not a unit circle, so we can't do that. Never mind. We'll review that when we get to number 97 in part 2. I wasn't thinking. Okay, cotangent, secant, and cosecant, they're easy because they are simply the reciprocals of these. Tangent being the reciprocal of cotangent, so we have here for cotangent negative 12/5. Secant, the reciprocal of cosine, so it's 13/12. And cosecant, reciprocal sine, so it's negative 13/5. And we're done with that. So it wasn't so bad, was it? No, not really. We go on to number 44, more of the same thing. Again, this tells us exactly what quadrant our angle is in. It's between pi and 3/2 pi. It's between pi and 3/2 pi. We are in the third quadrant. And we know that the cosecant is negative 4. Well, if cosecant is negative 4, then what does that mean sine must be? The reciprocal of negative 4 is negative 1/4. Why do we care? We care because of SOHCAHTOA. Sine is opposite over hypotenuse. So, here's theta. Opposite over hypotenuse. Opposite is negative 1. Hypotenuse is 4. Now we find our missing side. This time it's not quite so easy as it was in the previous problem, because I've got to use the Pythagorean theorem this time. Let's just work right here. A squared plus b squared equals c squared. A squared being the unknown, we'll leave it as a. And b squared being negative 1 squared is 1. C squared being 16. Subtract 1 from both sides. A squared equals 15. Therefore, a is the square root of 15. Congratulations, we found the missing side, and it wasn't a big deal. But watch out, we're going that direction. It's negative square root of 15. In calculating these values, you can either consider this to be negative and that to be negative while the hypotenuse is always positive, or you can ignore that and just use all students take chemistry to figure out the sign in the end. The danger with that is you might forget to do that, as I was getting ready to do in the previous example. Alright, we don't need this anymore. Get it out of the way. You know, we really only need to find 2 more. Because once you found 2, the other 2 are just the reciprocals. Let's do cosine. Cosine being adjacent over hypotenuse. Adjacent over hypotenuse, that's negative square root of 15 over 4. Negative square root of 15 over 4. Tangent is opposite over adjacent. Opposite over adjacent. That's negative 1 over negative square root of 15. But of course that turns positive. But as you know, we can't leave it that way. You can't leave a radical in the denominator. Don't be silly. So we have to multiply by square root of 15 over square root of 15, which gives us square root of 15 over 15. So that's our tangent. Square root of 15 over 15. All right, cotangent, reciprocal tangent. Hey, just a moment ago we knew that this was equal to 1 over square root of 15, right? So just flip that, so that makes this one square root of 15. Done. And secant, secant being the reciprocal, I did go over there, secant reciprocal of cosine, so flip this guy, that's going to be negative 4 over square root of 15, and of course you know the routine, multiply by square root of 15 over square root of 15, we get negative 4 square root of 15 over 15, negative 4 square root of 15 over 15, and we would probably prefer to write, put that fraction more like that. Oh, that's ugly. Negative 4 square root of 15 over 15. And as is frequently the case, not trusting myself, I just want to glance at the back of the book. This is number 44. Make sure I didn't do anything silly. Negative 1/4, negative square root of 15 over 4. Yeah, we're fine. Square root of 15 over 15, then square root of 15. They go in a different order. Tangent square root of 15, and then secant being 4 square root of 15, negative 4 square root of 15 over 15, and cosecant. Where in the world do they have cosecant? That was given to us. Okay. Yep, we're doing fine. We move on. Of course, you're hoping for a lot of those on the test because once you get the hang of it, they're pretty easy, aren't they? All right, this time. We've got to graph something here. Y equals 4 times the tangent of 2x. Well, before we do that, let's first of all just graph y equals tangent of x as a review. How do you graph y equals tangent of 2x? First of all, you remember basically what it looks like. It looks like this kind of thing, right? Oops, I'm killing things. It looks kind of like that, very, very roughly speaking. But we needed more detail, obviously. The period of tangent is 1 pi. But we know the tangent passes through 0, 0. It has a period of 1 pi. Shall we say half of it is going to be on this side and half on the other side. So if the period is 1 pi, we need to go a half pi this way and a half pi that way. So we need to go a half pi this way and a half pi that way. Of course, we remember that it has asymptotes. Tangent and cotangent has these asymptotes. So we go a half pi to the right, asymptote, a half pi to the left, asymptote, and it passes through this point. It also is going to pass through, halfway between the asymptote and 0, it'll pass through 1. Where is that, by the way? It happens to be at pi over 4. This is a half pi, that's a fourth pi. So it passes through 1, and it passes through negative 1 right there. Connecting those and put it in our asymptotes very neatly here. And we get something that looks like that. Of course, it is periodic, obviously. So the same thing repeats here in the space of another 1 pi, from a half pi to 1.5 pi, passing through this point, passing through this point, passing through this point, and we have another one, and another one, and another one, and another one. Now that obviously is not what we're trying to graph though. We're trying to graph 4 times the tangent of 2x. Let's undo all this beautiful stuff I just did. And let's do tangent of 2x. Forget the 4 for the moment. Let's do tangent of 2x. Then we will do y equals tangent of 2x. So what's the period of y equals tangent of 2x? Remember, the period is for sine, cosine, secant, and cosecant. The period is always 2 pi. For tangent and cotangent, the period is only 1 pi. So the formula for the period is pi divided by omega. What's omega? Omega is that coefficient of x right there. So the period of this one is not the normal pi, but it's pi divided by 2. So our period is pi over 2. So we have to squeeze the entire thing in a space of pi over 2. But if the entire thing is pi over 2 wide, then that means we must go a fourth pi to the right and a fourth pi to the left. So we go a fourth of a pi to the right and a fourth of a pi to the left. Those become our new asymptotes. Because between negative 1/4 and positive 1/4, we have a space of 1/2 pi, which is exactly what we need. We also know that it's going to, as usual, go through 0, 0. And halfway between 0 and the asymptote, it has to go through 1. And halfway between the 0 and the left asymptote, it has to go through negative 1. And so we end up with something kind of like this. What does that 2 then do? That 2 squishes the whole thing. It compresses it horizontally. By the way, a fraction here will stretch it horizontally. But a whole number, a number larger than 1, will squish it, compress it horizontally. So we now have a compressed graph, which obviously repeats every 1 pi. I'm sorry, every half pi. So another half pi, a fourth here, a fourth there, another asymptote, another asymptote, another asymptote. Okay. But that is still not what we have. We don't have tangent of 2x. We have 4 times the tangent of 2x. What does that mean? They're just trying to make your life miserable. I won't be this mean to you on the test. What this means is that it still goes through 0, 0, but instead of going through, that's a half, that's a fourth, this would be an eighth pi 1, it goes through an eighth pi 4. This point just moves up 4. This one moves down 4. So what does that do to us? It gives us a tremendously, whoa, I really messed that up. That was pretty bad. This one's kind of hard to do a sketch of. We get a tremendously stretched function. That's all the 4 does. And of course it repeats. So here, between the asymptotes, it passes through 0. It doesn't go through 1 and -1. It goes through 4 and -4. And we have this, and we have, and I'm not going to draw anymore. It repeats how far? Forever. Both to the right and to the left, it repeats forever. Let's go on to the next one. Okay, we're looking at y equals 4 times the secant of 2x. All right, before we do secant of 2x, let's do cosine of 2x. Because secant and cosine are reciprocals. That's significant. So, to do cosine of 2x, we know something about cosine. Cosine does not start at 0. Sine starts at 0. Cosine starts at 1 instead. Now we need to know its period. And we have a good feel. We know what cosine looks like. It looks, you know, it's going to, yeah, that kind of thing. Oh, that was awful. But you get the idea. Now, we want to do cosine of 2x. So what's the period? We've got to know the period. The period is, for sine and cosine, and their reciprocals, it's 2 pi divided by omega. Omega is 2. Omega is 2. So this cosine function has a period of 1 pi. So we've got to squeeze 1 complete cycle in the space of 1 pi. So if it starts here, it has to end in the same place 1 pi later. Right there. And of course, if it has a maximum point here and here, it must have a minimum point halfway between. There's got to be a minimum point down here. And what are you going to find halfway between the maximum and minimum? You're going to find a 0 and another 0. And we have a nice looking cosine function. Cosine of 2x. We really should continue that. Let's see, we've got a 0 there, a 0 there, therefore there must be a 0 there, and a 0 there, and a 0 there, and a 0 there. And it's going to do something like this, and it repeats that forever, in both directions. Let's not forget the negative side. Don't forget the negative side. Okay. All right, so that is cosine of 2x. But we don't have cosine of 2x. We have 4 times the secant of 2x. Do you remember? And you probably do. It's one of the more interesting functions. Do you remember how to graph the secant function? You start with cosine, but then, remember, for secant, everything that was a 0 becomes an asymptote. And your maximum and minimum points don't move. So secant is these crazy looking things like this that have a local minimum point here, a local maximum there, a local minimum here, a local maximum there, but have these asymptotes where the cosine function used to have zeros. So it looks kind of like this, and it looks like this, and it looks like this. Be careful not to cross your asymptotes, please. Don't cross your asymptotes. No matter how sloppy you might get, don't cross your asymptotes. Good advice to tell your grandchildren. Now, children, never cross your asymptotes. All right, at least not your vertical asymptotes. Now, children, you can cross your horizontal asymptotes, but never cross your vertical asymptotes. Good advice for your grandchildren. We're still not done. What about that 4 times the secant of 2x? This is the secant of 2x. We want 4 times that. So everything gets stretched by 4. Oh, so how do we graph that? It gets kind of nasty looking. Let's do it in green. Hope the green stands out well enough. Instead of starting at 1, we start at 1, 2, 3, 4. So it's going to be up here, and everything gets stretched, so it's going to be real skinny, real skinny. So there we have that one. This one, instead of being there, 1, 2, 3, 4, so I can't even put it there. 1, 2, 3, I can't put it there either. 1, 2, 3, oh yes, I was counting wrong. Learn to count, okay. Yeah, I can do this one too. There. And this one shows up here. So the green stuff is your actual 1, 2, 3, 4. The green stuff is your actual answer. The green stuff is your answer. The red and the yellow were just helping us get there, but your actual final graph is the green that you can barely see because my scale is kind of not right. All right, that's all there was to that one. It wasn't nearly as bad as you might have thought, right? Right, just take it a step at a time. Start with what you know. Start with cosine. Then understand how to do cosine of 2x. Find the period. And then figure out what happens when you do the secant, where you reciprocate everything. And then multiply it by 4, and you've got it. It wasn't so bad. Tedious, perhaps? One might say tedious. Okay. 64. Oh, they gave us something really easy this time. They don't even want us to graph it. We could with great ease, but all we have to do is get the amplitude in the period. No big deal, right? Right. Amplitude is, the divisible 1. Amplitude is 1. Period is 2 pi over omega. What's omega? Omega is 2. So the period is just pi. Done. One complete cycle sits in the space of pi, and it has an amplitude of 1. We could just do a quick sketch of it here. If that's 1 and that's negative 1, and if this is pi, then we would have 1, and remember, sine starts at 0. Sine starts at 0. Yes, graphing this is optional. They didn't tell you to graph it. So it starts here, and 1 pi later, it ends there. Halfway between it crosses again, and then it's got to go through your maximum and minimum points here. And there's 1 cycle. And of course, we could continue it indefinitely. And there is your graph of sine of 2x. Another one where all they want is the amplitude and the period. Amplitude, don't you tell me on the test that the amplitude is negative 2. There's no such thing. Sorry. The amplitude is the absolute value of A. It is the absolute value of negative 2. The amplitude is just 2. Do not, if you tell me on the test it's negative 2, I'm sorry, you lose points. The amplitude is 2 by definition. What's the period? Well, 2 pi divided by omega. What's omega? Omega is 3 pi. Be careful. It might be tempting to just say 3, or it might be tempting to include the x. No, the omega is the coefficient of x. It is 3 pi. We put 3 pi down here. So what's that do? The pi's cancel. We have an amplitude, we have a period of 2/3. Done. If you're graphing that one, you probably want to switch from using fractional parts of pi on your x-axis to using whole numbers on your x-axis. Then just squeeze it all into 2/3. Or you could divide your axis into thirds, 1/3, 2/3, 3/3, 4/3, and squeeze the whole thing into the space of 2/3. Oh, and of course, what would this do? This would make it twice as tall and twice as low. 2 up this way, 2 down that way. But that negative sign, what would that do to it? Cosine normally looks like this. That negative 2 is going to make it twice as tall, but also the negative would make it start down here, not at negative 1, but it will start at negative 2, and it will do something more like this. So the negative, the purpose of that negative 2, or the function of the negative 2, it flips it upside down and moves the minimum point to negative 2 and moves the maximum point to positive 2. We still have the same period, which in this case turned out to be 2/3. So that would be 0 and 2/3 is there. Okay, we now move on to what was next. I have no idea. Is there one more graph? Yes, we're graphing. Oh, they also have specifically asked you for the amplitude and the period. Well, no big deal. Amplitude is 2. And the period, why do they use T for period? I don't know. The period is 2 pi over omega, but omega this time is 1/3. Omega is 1/3. To divide by 1/3, we multiply by 3. So that's 6 pi. Your period is 6 pi. So in the space of 6 pi, we will fit in 1 complete cycle of cosine. But wait just a moment, it's 2 times cosine. So we're not going to use 1 and -1 as our maximum and minimum values. We're going to use 2 and -2 as our maximum and minimum values. And we got to get the whole thing in the space of 6 pi. Remember I said earlier, putting a fraction here makes the function get wider. Whole numbers scrunch it, fractions expand it. So it's going to be very wide. All right, so first we want to figure out where will the zeros be. Of course, sine and cosine, well, this is not a 0. Oops, not thinking. Because it does not start at 0, but it's going to start at 2, positive 2. It'll end up at positive 2 by the time it finishes one cycle. So I've got to move that point, I said pi, up to here. Then halfway between the two maximums, we'll have a minimum, right? So what's halfway between 0 and 6 pi? That would be 3 pi. We have a minimum at -2. And what happens between the maximum and the minimum? You'll have a 0. What's halfway between 0 and 3 pi? 1.5 pi. And halfway between 3 pi and 6 pi? 4.5 pi. Remembering that my, zeros. There we go. Yep, that's all there's to it. Now we just connect with our nice smooth curve. And you've got it. And we probably should continue, but it's hard to do that. It's going to go through here. And here it's going to go off the scale. And there we have 2 times the cosine of 1/3 x. So cosine made it start here instead of here. Sine would have started here. Cosine starts up there. The 2 makes it start way up there instead of down here at 1. And the 1/3 gives us a period of 6 pi, so we fit 1 complete cycle into the space of 6 pi. From here to there, we have 1 cycle. I've had some folks in the past who've been confused about what's meant by 1 cycle. Well, you start here, you end in the same place, and then repeat. So 1 cycle is when you start here, you end here, and then you repeat. All right, let's see what else we have here. Was there something else? 76. Oh, this one's kind of fun. They gave you the graph, and we come up with the equation. Well, that's kind of fun. We can see immediately we have an amplitude of 4. And it's going up, not going down. If it were going down, it would be a -4, but it's going up, so it's a +4. So we already know our function will start with 4 times something. 4 times what? Well, this starts at 0, 0, and it has that familiar sine shape. It's going to be 4 times sine. Now we just need to know what the period is. Well, or what omega is. The period is back where we started, then it repeats. So we have a period of 8 pi. 1 complete cycle in the space of 8 pi. So we know that the period, 2 pi over omega, is 8 pi. Solve for omega. Multiply by omega, divide by 8 pi. The 5 pi's cancel, we get 1/4. So we have 1/4 x done. 4 times sine of 1/4 x. And no, that 4 and that 1/4 are not related. It's just coincidental. I almost wish they had made it 3 instead of 4, so no one would get the impression that there was a relationship there. There is no relationship. but it was actually 4 because I really had it way up there. Okay. What if it had been way down here instead? Then we would just make that a negative 4. Oh, the book does also refer to phase shift. To save time and mental anguish, we skipped over phase shift. But phase shift is if we were to add or subtract something inside the parentheses. Actually, you're familiar with this idea. Suppose we were to add 1/4 pi inside the parentheses. Remember what adding something does when you do it inside the parentheses? It moves it to the left. So if we said plus, I forgot what I said already. Did I say 1/4 pi? I don't know what I said. If we said plus 1/4 pi, we would just take the whole thing and shove it 1/4 pi to the left. So it would be a phase shift. We can also move the whole thing up or down by adding something. If I were to put a plus 3 on the end here, I would just take the whole thing and shove every single point up 3 units. The minimum points, the maximum points, the zeros, everything up 3 if I put a plus 3 on the end. Would not be a very difficult concept, but we skipped over it just to save time. And is that the end? I think that's the end. Yep. Part 2 of your review assignment. You'll find this to be fairly short. These are a bunch of conversions of changing degrees to radians and radians to degrees. We haven't reviewed that yet. That's what this is all about. And then number 97, you're taking a unit circle that's been divided for you into parts like this. And you are going to both come up with the radian measures of each of these locations. And I think they also ask you for the coordinates of the terminal points. The coordinates of these points. Well, to do that, you need to remember your basics of the 45-45 and 30-60 shortcuts. And from there, you can figure out these coordinates for each one. So that's what number 97 is all about, simply filling out this unit circle. And these guys are just converting. Remember the conversion, you're going to multiply either by 180 over pi or multiply by pi over 180 to convert these things. You'll remember that when you get into it and start looking at these things. If you don't, you can always flip back in the book to see what the rules are. Okay, we're done. And again, the test. Originally, I was thinking about having the test this coming Friday, but that's not going to work out. And because we are required to have tests only on Fridays for math classes and science classes, we have to wait all the way until May 1st for the test. I'm also planning, at the request of at least one student, to have a Zoom review session sometime next week for those who are interested. Not required, just for those who are interested in getting together face-to-face so you can ask questions and clarify things. All right, so that'll be sometime next week. And that's it. See you later.